All right, welcome back. Let's continue our story on absolute age dating. So, still kind of in this kind of isotope radioactive decay chemistry realm, let's talk about half-life. This becomes important when we're trying to date, absolute date rocks and geologic events. The half-life of a radioactive isotope is the time it takes for half of the original unstable parent isotopes to decay to the more stable daughter isotopes. So it's that time frame which half of the original material is parent material is now decayed to the daughter isotopes, the stable daughter. Just half the material, not all of it, just half of it. The half-life of specific radioisotopes is constant, again, and it's been measured precisely in lab settings. There are different lengths of half-lives for different isotopes of different elements. It can range from just a fraction of a second all the way up to billions of years. So what is it? All right, so again, half-life is the time it takes for half of the original parent isotopes to decay, half of them to decay to the now stable daughter product. So if it's all parent isotopes, then there's, for instance, if you count, there's 32 parent isotopes and 0 daughters. There's 100% parents, 0% daughters. No half-lives have been undergone. This is just brand new rock that just formed. After one half-life, half of the parents now become daughter products. There's 16 parents and 16 daughters, 50 and 50%. That's one half-life. That's the time it took for half of the parent material to become daughters. 2 half-lives would be, now that we have 16 parents, half of that. So if we're going from half of 32 is 16. Half of 16 now, let me move me a little bit, is 8 parents, 24 daughter products. So we keep cutting this number in half. So that leaves 25% parents, 75% daughters. So that's what it's meant by half-life. The time it takes for half of whatever parent isotope is there, unstable parent isotope, to decay to the stable daughter product. And then now half of what's left. And then so after 3 half-lives, we would have 4 parents and 28 daughters. After 4 half-lives, we would have 2 parents and 30 daughters. And so it's half of kind of what's left. Okay, so different isotopes have different half-lives, the time it takes for half of the parent material that's left to decay to the daughter product. They range from small amounts of time to large. See, on this scale, so this is just in billions of years, because there's some that have a half-life of just a fraction of a second, which wouldn't be useful in dating. But for instance, potassium decays to argon-40, and half of that, the half-life of where half of the potassium would decay to argon takes 1.25 billion years. U-238, the time for half of the original parent U-238 to decay to now stable daughter lead isotopes is 4.47 billion years. So as a little example, let's look at U-235 when it decays to lead-207. The time for half of that parent material to decay to the stable lead takes 0.704 billion years, or 704 million years. So that's after one half-life. Then half of whatever's left of the uranium, if that decays, that's 2 half-lives. So 1.4 billion. Then half of what's left, once that decays to daughter product, so now that's 3 half-lives, 2.1 billion. Half of what's left decays to daughter, 4 half-lives. Half of what's left decays to daughter, 3.5 billion years. So you're just multiplying. So however many half-lives it's gone through, you just take the half-life time and multiply it by how many half-lives. So 2 half-lives, so 0.704 times 2 is 1.408 billion. 3 half-lives, you just take this times 3. 4 half-lives, this times 4. 5 half-lives, this times 5. Probably go over some of this, these types of problems in lab. I'll kind of walk you through those once we get there, if we have them. I still have to make the lab. So when we look at that graphically, so parent isotopes decay by 50% after one half-life. So half of 50%, so after two half-lives, there's only 25% of the original parent. Half of 25 is 12.5% after three half-lives. Half of 12.5 is 6.25 after four half-lives, and so on. So we have this kind of exponential decay or exponential growth in the daughter product. Usually as we get towards 7, 8, 9, 10 half-lives of time, the particular isotopes becomes unusable. So that's why we want to choose one with a proper time length to help best date the material. Now when we use this material, and I'll show you how it's done, when we use this material, we don't use just kind of one. We usually use multiple isotopes and count the parents and daughters of these multiple different ones. We might use 235 and 238. And so we use both of them, or multiple, two or more, and if they all give us the same value, even with the mathematics working out differently, then we know we're on the right track. And so that's what we use. We use multiple different ones just to make sure everything checks out. We don't just use one and then say we're done. So again, if we have 0 half-lives, the rock's brand new. If we're looking at a particular mineral, then all the elements are parent isotopes after one half-life, so that's half of 50%. Now we're down to 50% of the original parent material. So half of this, so one line, turned to daughter. So now we have this top row, so after another half-life, so half of that, so 5 turns to daughter. Now after another half-life, so 5 now becomes 2.5. Now we're talking billions of atoms, so we're just using 20 as kind of a example. But again, as you get further and further in half-lives, you get less and less parent, and then it gets a little bit harder. So we want to choose a particular isotope that has the right time scale. So by measuring the parent and daughter ratio and knowing the half-life of the parent based on what we know from labs already, and we count all of these things up using fancy machinery, we can calculate the kind of absolute age of a sample of rock containing the radioactive element. The ratio of parent to daughter isotopes in a particular sample, we use something called a mass spectrometer. That's the fancy machine, expensive machine I've been alluding to. It's an instrument that measures those proportions of atoms with different masses. Kind of somewhat as simple as I can put it. So here's a mass spectrometer, very big, very expensive machine. So you get the sample of rock material. Usually you crush it up so it's easier to vaporize. So you have a heat source and some energy source. We run through it, and as that material kind of goes through some magnets, it spreads this material out, and there's a let me move this over here. So the magnetic field helps to deflect and separate out all of these different isotopes, and the detector at the end then just counts them all up. Okay, you have 1 billion parent atoms in this, and you have 2 billion daughter atoms in this one. So it just counts it all for you. And then, with some computer imaging or computer software, it just kind of spits it out. Oh, this thing is 2.5 billion years old. Beautiful. So that's how we do it. Science is awesome. Move me back. So an example. All right, let's look at a little bit of an example. So let's say we're looking at a rock, and this is maybe something we'll tackle in lab. And a rock has a parent-daughter ratio of 1 to 3. There's 1 parent left and 3 daughters. All right, there's 1 parent left and 3 daughters. And we know the half-life of the particular isotope we're looking at is 57 million years. All right, so I have 1 parent and 3 daughters, and I know of a particular isotope, and that isotope has a half-life of 57 million years. How old is that rock? Okay, so we take the ratio, which is a division, of how many parent I have left, which is 1, divided by the total I started off with, which is the parent plus the daughter. So I started off with 4 parents, and then I'm left with 2 parents after 1 half-life, and then I'm left with 1 parent after 2 half-lives. So you can do it that way, or mathematically you take how much parent I have left, 1, divided by the total amount of isotopes, parent plus daughter, 3 plus 1 is 4. So 1 divided by 4 is 0.25 or 25%. Graphically, I can now come over to this graph. So 25% of material left is parent isotopes. So 25% is associated with 2 half-lives. So if 1 half-life is 57 million years, then multiply that by 2, so then 2 half-lives is 114 million years old. This rock is 114 million years old. Again, mass spectrometers, computers do all that, pretty instantaneously. But it's good for the soul to do these things kind of by hand, so we may look at some of these half-life calculations, figuring out the age of rocks in lab. I'll try to keep it as simple as possible. Let's go ahead and pause there. When we come back, we'll talk about, what kind of material can we actually date? We can't really date all kinds of rock material. Only certain rocks and in certain conditions give us proper dates. We need to know what those are. So when we come back, that's what we'll talk about. I'll see you back in just a second.